This is a little simulation where we can look at the collision between two carts. I can change their initial velocity, I can change their masses, and I can change the type of collision. This is going to be a collision called an elastic collision. I would like for you to know what elastic collision means. It means that the objects perfectly bounce off of each other. It has a little bit of a deeper meaning that has to do with kinetic energy and things like that. But for the purposes of this class, elastic, just think of things perfectly bounce off of each other. So this is interesting. I want to show you what's going to happen here. If I have carts that are identical to each other, the mass of this one is 1 kilogram, the mass of this one is 1 kilogram. They're moving at the same speed, but in opposite directions, 5 meters per second to the right, 5 meters per second to the left, -5. What do you think is going to happen after they collide? So we know that the total momentum of the system cannot change. What is the total momentum of the system? Well, interestingly enough, remember, how do we find momentum? Mass times velocity, so 1 times 5. The momentum of this cart will be 5. The momentum of this cart, 1 times -5, will be -5. If we add those together, the total momentum is actually 0. So the total momentum of my system should remain 0. Let's see what happens when they collide. Did you see that? They perfectly swapped velocities. I'll do it one more time. So the one that was moving to the left initially with a -5 meter per second velocity is now moving to the right. And this object, which was moving to the right with 5 meters per second, is now moving to the left, negative. So we can think about this collision if the objects are perfectly the same mass, perfectly the same velocities. All they've done is transferred velocity. They've transferred their momentum. This one now has a momentum of -5. This one now has a momentum of 5 times 1, 5. What's the total momentum? It's going to be 0. That has not changed. So that is a pretty interesting result. They've just swapped velocities, swapped momentum. So momentum can be transferred. And it's all because the total momentum of the system cannot change. Let's see what happens if I make this object much more massive, 3 kilograms. What do you think is going to happen? Let's see. So that was really interesting. This one actually stopped and basically gave all of its momentum to this guy here. Let's see if we can think about why that might be true. Well, what is the total momentum of the system? Momentum is mass times velocity. So over here, this moving cart, 5 meters per second, its mass is 3, that momentum is 15. Over here, this moving cart, -5 meters per second, 1 kilogram, that's -5. So 15 and -5, what is the total momentum of the system? 10, right? So let's see what happens. This one, after the collision, goes off with a speed of 10 meters per second to the right, +10 times 1, so that's a momentum of 10. This one now has a momentum of 0 because its velocity is 0. So before the collision, the total momentum was 10. After the collision, the total momentum is 10. And it makes sense that the more massive object would kind of have a larger effect on the small cart. The small cart ends up being affected more because this one is carrying more momentum. Remember, the whole point of momentum is that talking about an object's velocity is not enough. We also have to talk about how big it is. How much stuff do we have moving? Well, here we have more stuff moving. It has a larger momentum, so this cart gets affected by the collision more. This is a type of collision called an inelastic collision. Basically, for your purposes, you need to know that an inelastic collision is when the objects stick to each other. They stick together. So here's what I mean. These objects are coming together and they stick together. They stick to each other. In an inelastic collision, the momentum is still conserved. Turns out that energy, kinetic energy, is not conserved in an elastic collision. We'll talk about energy a little bit later. Let me switch this. An inelastic collision here. They stick together. They're now moving with the same velocity. Let's see if we can actually solve this. When we're talking about inelastic collisions, these are actually easier mathematical problems to solve. So I want to take this exact scenario and see if we can't figure out what the resulting velocity will be. This is easier because at the very end, both carts are moving as if they are one. They have stuck together, so they both have the same velocity. They both have a single velocity, so all we have to do is solve for one velocity. Let's see if we can figure out if we can mathematically show that this final velocity should be positive 2.5 meters per second. Okay, so here I've drawn the exact same scenario. We have two objects. They're moving on a collision course. They're going to collide with each other. Object 1 over here, moving to the right, has a mass of 3 kilograms, moving with a velocity of 5 meters per second. This object is moving to the left, negative velocity, 5 meters per second, and it is less massive. It only has a mass of 1 kilogram. So if this is an inelastic collision, do you remember what that means? That means that the objects, after they collide, they will stick together. They will stick to each other. What if I wanted to know the final velocity? The final velocity after the collision? Well, I've got to use the conservation of momentum to think about this, because before they collide and after they collide, it does not matter that they stick together. Before and after the collision, the total momentum will be the same. So I can make this statement. I can say the momentum before the collision is going to equal the momentum after the collision. And let's start thinking about how I can turn these into bigger expressions. Before the collision, the momentum is very simply going to be the momentum of object 1 plus the momentum of object 2. So I can say that's going to equal my final momentum. And I know that the momentum of object 1 is mass times velocity, 3 times 5, m1 v1, plus m2 v2, velocity of 1, velocity of 2. That's the mass times the velocity for the second object. So very simple. I'm just using the mathematical definition of momentum, and I know that's going to give me the initial momentum before the collision. And because momentum cannot go away, it's a conserved quantity, that's got to equal the momentum after the collision. Let's start plugging numbers in. 3 times 5 is 15. Mass 2 is 1. My velocity here is negative 5, so it's going to be a negative 5. So it turns out that the momentum of my entire system before they collide is 10, and that's also going to equal the momentum after they collide is 10. Well, how does that help me? Well, think about it. After they collide, they have really stuck together to become almost a new object. So, because it's an inelastic collision, they have stuck together, and now maybe they're going to move. So how are these objects going to be moving together? That's what I'm trying to find, the final velocity after the collision. Well, I know that this system has got to still have a momentum of 10. What does momentum mean? That means mass times velocity, right? Well, what is the mass that I'm talking about? What is the mass of this object? Pretty simple. What is this object composed of? After these spheres collided in an inelastic collision, they stick together. Here's sphere 1, here's sphere 2. So what is their mass? It's going to be just the total. So my final momentum is going to be m1 plus m2. That's the mass of my new stuck together object times what? The velocity. And that's going to be their final velocity that I'm trying to find. How come I don't need two velocities here? Well, because these objects are stuck together. They are moving as one. So now I can start plugging numbers in pretty simply. My final momentum is 10. How do I know that? Because I solved for the initial momentum before the collision. Momentum is conserved, so the momentum after the collision is still 10. Equals, I know that the total mass of this object after they collide and stick together is going to be the mass of 1, which is 3, plus the mass of 2, which is 1. That's going to be a 4 times my final velocity. Divide both sides by 4. My final velocity should be positive 2.5 meters per second. Okay, so what? What the heck does that mean? That means that after these two objects collide and stick together, this one object is going to keep on trucking to the right with a velocity of 2.5 meters per second. Does that make sense? It actually does make some pretty good sense because the larger object, the more massive object, was carrying more motion with it because it's bigger, and so it's going to have a greater effect. The smaller object is going to be forced to stop and turn around and move to the right. So both of these are going to be moving to the right. So my final velocity is a positive 2.5. I believe that is indeed what the simulation showed. And now both of them are one object. That object is moving with a velocity of 2.5 meters per second to the right.